Welcome to the OSVVM 15-minute waltz. Let's go ahead and get started. What is OSVVM? Well, first up, it's a verification framework. It's a verification utility library that implements the things that make VHDL a full verification language. It's a verification component library with a growing set of verification components. It's a script library that allows us to write simulator-independent scripts. It's a co-simulation library that lets us run software on top of our hardware in the simulator. It generates test reports, so HTML for humans and JUnit XML for continuous integration tools. OSVVM is free, open source, available on GitHub, available on osvvm.org, and it's developed by the same VHDL experts who have helped with VHDL standards. As a framework, it looks very similar to the System Verilog framework. We have verification components that implement interface signaling, and we have a test sequencer that has sequences of transactions that implement our test case. Then each test case is a separate architecture of test control. Our framework is simply structural code, and it's simple, just like RTL code. So we have an instance of the DUT. We have instances of our verification components, and we have an instance of our test sequencer. Elements of our framework. We have transaction interfaces, such as manager rec. We have the transaction API, such as write and send. We have verification components, and we have the test sequencer. We have our model independent transactions. This comes from the observation that many interfaces do similar things. So OSVVM has codified the transaction interface and transaction API for stream interfaces, such as AXI Stream and UART. And in there, you'll find our transaction interface implemented as a record and our transaction API implemented as procedure calls. These procedures here are a subset of what's in the OSVVM library. And then we have another set for address bus interfaces, or what's also called memory mapped interfaces, such as AXI4 or Avalon. And again, we have our record and our transactions. And again, this is a very small subset of what's in the library itself. The benefit of this, we simplify verification component development. We simplify the reuse of common test cases and sequences. Our verification components have a DUT interface, such as the record shown here for the AXI bus, or it could also have individual signals. And then it has a transaction record on it that uses one of the types from the previous slide. So here we're using the address bus rec type. Inside the verification component, if it's a very simple one, we're calling wait for transaction, which waits until a transaction has been called, and then the record has something in it. So we decode the record and do the operations. Now, we don't often have subprograms in here. More often, I write the code in here. Benefits. For verification developers, they just focus on the model functionality and don't have to do the other stuff that's provided by the OSVVM model independent transactions. Our test sequencer has transactions on the interface and maybe also reset. Inside, this is where our test case is, and our test case is in a single file. We have a control process that initiates and finalizes transactions. And then we have one process per interface. So we're concurrent, just like the design is concurrent. Our tests are simply calls to the transactions. And it's easy to add and mix in directed tests with constrained random tests, with scoreboards and functional coverage. We also have synchronization utilities that help us synchronize these independent processes, such as here at the beginning or here as the test is done. As we're running the test, we're checking for errors and such and recording them against a data structure. And then at the end of the test, The control process calls this end of test reports procedure that reports all of the errors for the test and creates YAML files that the scripts convert into the HTML reports. Writing a directed test is easy. We simply call the transactions such as send on the TX side or get here on the RX side. We can do some checking with affirm if equal from the alert log package. We can do checking by instead calling the check transaction from the transaction interface. The test output of the affirm if equal then, if it passes, produces a log passed. If it fails, it produces a log error, an alert error. The benefit here, we've greatly simplified writing self-checking tests and we've improved readability. Our constrained random tests are simply a call to something from our randomization library, such as our distant here. And this one, 70% of the time, it's going to generate a 0 for us. And in that case, we're going to generate no errors, and we're going to pick a data value between 0 and 255. Other possibilities, 1 for parity error or 2 for stop error. Note, we set up the operation to be stop error, but we also randomize a different set of values. This is the nature of constrained random. And then we do our transactions. So here we're setting up our transaction and we're calling at the end, but we could also be calling it within those case branches and could be doing more than one transaction per branch. So our constrained random approach in OSVVM then is randomization plus code plus transaction calls. Now, we could do the checking the same way we were previously and repeat the sequence on the receive side, but we really don't want to do that because it's tedious and it's error prone. Instead, we can use a scoreboard. A scoreboard is a data structure used for checking data when it's minimally transformed, such as sending something across a UART, receiving it somewhere else like we're doing here. Our scoreboard has a FIFO and a checker inside. It uses package generics so that we can support different types. It handles small data transformations. It handles out of order execution, and it handles dropped values. Using a scoreboard is pretty easy. We set up an object of the ID type, and then we construct the data structure. So we're building this in the package, and it's actually a singleton data structure that we have sitting out there. Then we call push with the handle for the scoreboard, SB here, and then we do a send transaction. And then the receive side, we do a get transaction to receive the value, and then we just pass the values that we received up to the scoreboard for checking. So we have a big benefit here in that the checking side is relatively generic and it stays the same even if the stimulus generation side changes. So we switch from directed to randomized test, still the same thing on the checker side. The next thing we need to have is functional coverage. Functional coverage basically is code that tracks items in your test plan, such as requirements, features, and boundary conditions. Why do we do this? Well, with randomization, how do you know what the test did? Okay, so we're looking for 100% functional coverage, 100% code coverage, and that what indicates that test is done. Now, why not just use code coverage? So code coverage tracks code execution, but it misses anything that's not directly in the code, such as binning values from a register or things that are independent that we need to correlate. Okay, so here we're building out our coverage model again using an ID type because again, the coverage models are in a singleton data structure. We then construct the data structure and then we define the coverage model by defining the bins of values that we want to see. And then we call iCover to collect the coverage. And it's simple. In fact, functional coverage with OSVVM is as simple and concise as language syntax. Now, we also go further. We can do introspection of the coverage model and create what is considered to be runtime coverage-driven randomization, We call this intelligent coverage randomization, which is what we're doing internally is randomizing across the coverage holes. So we start out the same way. We create our coverage object, we do our call our constructor, and then we build out our bins. But now we add to our bins coverage goals. These become randomization weights, and then we call up get ran point with the coverage model to randomize a value within that coverage model. And then we decode that value much similar fashion to what we did with the constrained random approach. And then we dispatch our transaction and we record the fact that we did that transaction with iCover. When we finish our test, we're going to generate our reports. The first reports you're going to see are these pass-fail tests for a given test, but end of test reports is also essential for our other reports generated by OSVVM. The next thing we have is our scripting, and our scripting is started out as a list of files, and then it evolved to having these tickle procedures that we call to set up our tests. So we have our library and we activate our library, and then we analyze to compile things, and then we simulate. And note, when we activated the library, we use that same library for the rest of the commands that follow it. So the library is set and remembered, and we work on basically all of the popular VHDL simulators with the exception of Xilinx's XSIM. We're waiting on them to get good 2008 support. We call our scripts using build and include rather than tickles source and EDA vendors do, because this is what allows us to, when we specify a path, to make the path relative to the script directory rather than making it from relative to the directory the simulator's running in. That's important because you want to be able to relocate things on a project by project basis. So we use build to start things off, to call things from the command line, or to call the top level scripts from the continuous integration run. And build plus end of test reports is what generates our reports. And then include is for calling a profile from another profile. Our report, we're going to just show you one of the reports. Our build summary report starts out with status for the entire build. Did it pass? Did it fail? We give you links to the log file and an HTML version of the log file. If you ran it with coverage, we have a link to the merged code coverage. We have a test suite summary, so we break our test cases out into test suites that focus on testing one thing, like the alert log package or the AXI stream verification component. And then, so that's a summary for the suites. And then we have the test case summaries that give us details of how each test case within a given suite ran. So all you need for your VHDL verification is OSVVM. We have a powerful, concise capability that rivals other verification languages. We have unmatched reuse through the entire verification process. We have unmatched report capability with HTML for humans, JUnit XML for continuous integration tools. We have tests that are readable and reviewable by all, meaning verification engineers, but also the hardware designers, but also the software and system engineers. If you can read the transactions, you can read the tests. OSVVM is set up to be adopted incrementally, and you can find us on GitHub. You can find us on osvvm.org. Thank you for attending my presentation.